This is 2011 paper 1 question 2, which is on complex numbers, and A part I of the question involves converting a number that's given to us in Cartesian form to polar form. So we have this number here, 1 minus I, and we're going to have to convert it to polar coordinates. Now if we come over here and just have a closer look, that number is 1 minus I, which is 1, it's really 1 minus 1I, think about it that way. It's written in what we call Cartesian form, which is in the form a plus b times I. So by corresponding, you can see straight away that the a corresponds to 1, and hopefully you can see also that the b, just be careful here, corresponds to minus 1. So that's the Cartesian form of the complex numbers. Now to convert to polar, we need to do some preliminary work first, and that involves getting what we call R, or the modulus of the complex number, and the formula for that is the root of a squared plus b squared, which in this case is the root of a, which is 1 squared plus minus 1 to b squared, and you end up getting the root of 2. Now we also have to get the argument of z. So I'm just, by the way, I'm just calling this number z here, just giving it a name. The argument of z is the angle it makes with the x-axis. Got to be a little bit careful here. We really need a diagram to see how things are. So an Aragon diagram. It's 1 along the x-axis, minus I, minus 1I in the 1 along the real axis, minus 1I in the imaginary axis. So our point is here, and there's R, which we just worked out to be root 2. And just keep in mind, when you're measuring the argument, which we call theta, you have to measure anti-clockwise always. You should know this from trigonometry, anti-clockwise from the positive sense of the real axis. So that's theta. And now from our knowledge of quadrants in trigonometry, to get theta properly, you're going to need to get a reference angle here, and we need to have a closer look at this right angle triangle to get that. That right angle triangle there, it has 1 unit along here and 1 unit here, because it's 1 minus 1I. So we can say that the tan of R is 1 over 1, which is 1. So R must be 45 degrees, or pi over 4 radians. Just make that clear, because there's two R's. There's a capital R and a small r, not to get mixed up. So that's capital R. The reference angle is pi over 4, and which means theta, as you can see from the diagram, is 360 minus that, and so it's equal to, so as we just saw there, it was the inverse tan of the b over the a value, and the full angle is 2 pi minus the reference angle, which is pi over 4. Of course, we can think of 2 pi as maybe 8 pi over 4 minus pi over 4, which is 7 pi over 4. So now we have it. The polar form is always written as r times cos theta plus I sin theta, which in our case R is root 2 and theta is 7 pi over 4. So we have our two values to fill into the formula, and that's it done. R is root 2 times the cos of 7 pi over 4 plus I sine 7 pi over 4. And that's part I done. Now in part 2, we come to the whole reason why you might need to get polar form in the first place. I mean, we could well ask the question, when you're given a number like z, which is 1 minus I, which is in what's called Cartesian form, why would you ever want to convert it to something like we just got there, which was at the end root 2 into cos 7 pi over 4 plus I sine 7 pi over 4. By the way, this is a good exam technique as well. You notice in part 2 I'm summarising what happened in part 1, and that might lead to a clearer understanding of what to do next. And what we do next is we use this theorem called the Moivre's theorem. Now, this is a theorem which is proved elsewhere in the course, so you need to look at the induction section of your course for the proof of that. But for now, we're only interested in the result, what it actually says, and it's a very simple result to use in a question. You just need to know this much for now, that there's a theorem called the Moivre's theorem. And it says simply, whenever you have cos theta plus I sine theta to the power of something, we'll say n, well the angle, or the power can just come down in front of the angle, so it becomes cos n theta plus I sine n theta. That's as much as you need to know for now. Hopefully you can see the power in this theorem, because it means that when you got a power that's annoying us, like this n here, when you've got a power and that's hard to work out, say a very high power like 10 or 20 or something, well, we can almost magically get rid of the power by having the power come down in front of the angle like that, and we no longer have this problem of working out a power. And that's precisely what we're going to do here with the number we got in the last part of the question. I mean, we have 1 plus I to the power of 9. Sorry, we have 1 plus I worked out from the last part. So there it is. Here. That's 1 plus I, 1 minus I. We're now going to work out that to the power of 9. So, in other words, z to the power of 9 is equal to all of that to the power of 9. Cos 7 pi over 4 plus I sine 7 pi over 4. So they're both sides are to the power of 9. Which means we've got a root 2 to the power of 9 times cos 7 pi over 4 plus I sine 7 pi over 4 to the power of 9. But for example, you can spot the following, that root 2 to the power of 9 is really root 2 to the power of 8 by root 2 to the power of 1. And over here is rough work, root 2 to the power of 8 is equal to root 2 squared to the power of 4. And root 2 squared is 2, so it's 2 to the power of 4, which is 2 2s is 4, by 2 is 8, by 2 is 16. So that's just give you a neater way than using the calculator of working out what we have here. So we have the 16 root 2 altogether. That's that part sorted out. Now in the brackets we can use the Moivre's theorem. The 9 comes down in front, so this power here, as we saw from the Moivre's theorem, we can bring it down in front of the angle, and you can get cos of 9 times 7 pi over 4 plus I sine 9 times 7 pi over 4, which is the cos of 7 9s is 56 pi over 4 plus I sine 56 times pi over 4. And that's a very important step, because that means that the power has disappeared. If we couldn't make the power disappear, look back to the original question we were asked, which is this. We were asked to work out 1 minus I to the power of 9. The only other way to do that without the Moivre's theorem would have been to multiply 1 minus I out, multiply it by itself 9 times. You'd be there a long time trying to actually get the answer. So it is very, very important that we have a rule like the Moivre's theorem to allow us to get rid of that power. Now, just to finish off this question here, that really is the most of it finished. It's just to tidy up really. You could think about it like this. It's 16 root 2 in front. Now the cos of 56, I like to think of this as 45 degrees. Maybe thinking degrees. And if you think about 45 degrees, how many of them is in a full circle? You're going to have 8 45s in a full circle. And so if 8 times pi over 4 means you're going all the way around. 7 8's 56 means you're going 7 times around the circle. So in other words, you're back to 0 again. 56 pi over 4 means you're actually back to 0. Because you're going 7 times around the circle. So that's really the cos of 0 plus I sine 0. And now it's 16 root 2 times the cos of 0, which is 1 in your tables, plus I sine 0, which is 0. And the total answer at the end is 16 root 2.